Okay, I think this is a good time to start. Um, well, before I start, or before we start, welcome. I'm Gustavo Bejar. I'm a PhD candidate at Michigan Tech, and I'm gonna be the host for this 2025 webinar series organized by CONVERSE Emerging Researchers. I'm gonna direct you to our website, converse-er.org, for more information about CONVERSE Emerging Researchers, and also to find the recordings for our webinars from last year, from last fall. You can find those also in that website. Um, Before we start, Michael has a few announcements. So Michael, I'm gonna pass it over to you.
Can you see my shared screen?
Yes.
All right, awesome. So just a couple of announcements before we get started. We're going to have an icebreaker at the AGU Chapman Conference. So mark it on your calendars for Monday, February 10th at 5:15 Hawaii Standard Time. We're really looking forward to that as part of that coming meeting and looking forward to seeing some new folks out there working on basaltic calderas. As Gustavo mentioned, we have a new website, so plug in that as well. We have a listserv, so if you want to join, I'll post a link in the chat in a second here. A plug for our next webinar coming up with Carmen on February 11th. I'm really excited for that one as well, so please tune in a couple of weeks. And then some general opportunities that have come across our listservs and email address and such. So if you have any questions about any of the programs or positions open here, please send us an email and we will send you more information. Cool, that's all I got.
Awesome. Thank you, Michael. All right. So, well, now it's a good time to introduce our speaker, our first speaker for this webinar series. This is Penny Wieser from, she's an assistant professor at UC Berkeley, and she's gonna talk about Thermobar, which is a Python tool that you can use to perform calculations for mineral melt, thermometry, chemometry, and so on. So, yeah, welcome, Penny. Thanks once again for being our opening speaker, and I'm gonna pass it over to you.
1 second, let me just get my PowerPoint going. Okay. Do you see presenter view or do you see regular view?
Regular view.
Regular view. Okay, folks. So what we're going to do is we're just going to do a little bit of an introduction to some of the theory behind Thermobar, and then we're going to go into doing an actual example, and that will either be you running Python locally if you've got it set up, or we'll be using the Victor server, which is what I'm going to be showing you how to do it on. And then if we have time, we'll do a little bit more theory afterwards. So just a quick introduction. Thermobar, actually, let me get rid of the floating meeting controls 1 second. Right. Thermobar attempts to help you answer some of the most fundamental questions in igneous petrology. So that might be things like how hot your magmatic system is. That is obviously very important if you do diffusion work, because anyone who's done that knows that your biggest uncertainty in timescales comes from the temperature that you're assuming when you're modeling that diffusion. Another question a lot of us care about is how deep magmatic systems are, how deep things are occurring at. So is your magma chamber located at 3 kilometers or 20 kilometers beneath the volcano? You might also be interested in how wet your system is, and we can address this using hygrometers. So did your magma have 1 weight% or 10 weight% water before it erupted? There are then some new methods where we can use the composition of minerals to estimate the melt composition. So you could get the approximate silica content of your system by measuring the amphibole. And then you might also want to answer questions like how viscous your system is. And Thermobar also contains some of the empirical models to make those calculations. So if we just kind of step back a little bit to the kind of theory, 1 second, sorry, the floating meeting controls come back up every time someone joins. So if we're trying to calculate pressure, we are basically looking for a chemical reaction that has a large change in volume that makes it sensitive to pressure. So for example, a common one of these is using clinopyroxene. And very specifically, the exchange of silica, sodium, and aluminum between the liquid and the clinopyroxene and what we call this jadeite end member. This reaction has a big change in volume. Now, you could approach this from a pure thermodynamic perspective. In reality, most of our thermometers and barometers are a mix of thermodynamics with empirical terms added. So just to kind of demonstrate what that means, you could basically write the thermodynamic equation like this. So pressure has a volume term and a temperature term and other thermodynamic terms. And then in reality, what you really do is you basically try and calibrate these coefficients. So you end up with an empirical equation that looks quite a lot like the original thermodynamic equation, but with these actual numbered terms. In reality, when you do barometers like this, they often don't provide a very good fit to the data. So people end up adding other terms. So for example, in this barometer from Keith Peterka, he has added empirical terms that are not in the root equation, but to account for the calcium and the silica content and the magnesium number of the liquid. And these help provide a better match to the experimental data. And that is fundamentally what these equations are calibrated on. You take experiments where you know the pressure and temperature, you would measure the jadeite content of the clinopyroxene, the equivalent component in the liquid, and from that you would then regress to try and work out what are the best coefficients that we can attach to this. And by adding all these different sort of like extra empirical terms, this is how we end up with so many different equations. So when we do the practical in a minute, you'll see there are probably 20 equations for CPX. A lot of them are based on this empirical framework, this thermodynamic framework, but the difference is they have different empirical terms and different coefficients attached to those terms. Now, what you'll notice in this equation for pressure, and this comes from the thermodynamics, is that there's a temperature term. And this is one of the big problems with thermobarometry is you don't just get to calculate pressure, you have to kind of know temperature, but in most natural systems, you don't know either pressure or temperature. So what you end up having to do then is also taking an equation for temperature, which again is rooted in thermodynamics, but with additional empirical terms. And you can see this temperature equation has a pressure term. So realistically, you end up co-solving or iterating these two equations so that you are calculating both pressure and temperature in an unknown system. And kind of similar to how the thermodynamics for barometers are based on finding a reaction with a large change in volume, thermometers are based on finding a reaction with a large change in entropy. So that's why when you look kind of at the basis of all these different barometers for CPX, a lot of them use jadeite for pressure and diopside Hedenbergite for temperature, because they are the reactions that have the most sensitivity. Okay. So what do these tools look like in the past? So Keith put together a fantastic set of spreadsheets with his models that he's released over like the last 20 years. And how these would work is you would paste in your liquid composition, you would paste in your clinopyroxene composition, and then you would scroll along to the end of the spreadsheet and you would see that there are columns for temperatures and pressures calculated using all these models. And this is fine, but not all of the models were present in this. So for example, if you wanted to do amphibole calculations, Rodolfi put together models which calculate temperature, pressure, oxygen fugacity, and water content from a measured amphibole composition in 2021. You would have to download a separate spreadsheet and paste your data into here. Again, this is fine, it's not super efficient though. Similarly, so Maurizio Petrelli put forward a machine learning method to calculate pressure and temperature using clinopyroxene in 2021. And if you wanted to run his model, you would have to download his Python script. You would have to put your data in a very specific way into his Excel spreadsheet. So for example, he wanted his liquids to be between column B and M. So you can see these tools were usable, but they weren't super interoperable and super comparable. So what we kind of decided to address was the fact that these tools require you to reorder data many times. So for example, if you want to use the amphibole models of Rodolfi, this is the element order it wants. If you want to use those of Peterka, you can see like chromium has been swapped around. So we wanted to sort out this data input because it's just tedious. We also wanted to address the fact that all of these models were spread across different environments. So some of them are in MATLAB, some of them are in R, some of them are in Python, and you would end up with like tons and tons of different Excel spreadsheets. And then I guess the real reason for building Thermobar was that these spreadsheet-based methods don't have any advanced functionality. So what you'll often find is if you want to calculate pressure and temperature from a clinopyroxene, you will need a melt composition that you think is in equilibrium with your clinopyroxene. Now, typically, when you look at an erupted sample, you might have 20 different clinopyroxenes, all of which have different chemistry, but you only have one liquid. And that liquid might only be in equilibrium with, say, the most evolved clinopyroxene that formed just before eruption. So people over the years have developed clever methods to try and match the measured clinopyroxenes to lots of different liquids. That might be liquids erupted over 10,000 years at that volcano or within the region. But in Excel, if you want to consider liquid 1 matching to every single CPX you've measured, you would have to have as many rows as you have CPXs, paste liquid 1 in, and then you would have to do the same for liquid 2 and liquid 3. So you would end up with spreadsheets with thousands and thousands of rows, and it's going to be really, really tedious. There was no real publicly available method to do this melt matching efficiently. So that was one of the things that we addressed in ThermoBar. There are also lots of oddities. Like, as I said, these barometers tend to have a temperature term and the thermometers tend to have a pressure term. But say you care about plagioclase liquid and you want to calculate water content. Well, the equations that have been published to calculate water from plagioclase liquid are extremely temperature sensitive. And yet this spreadsheet that is released for that calculation maybe doesn't have a thermometer built into it because they calibrated it based on experiments where they know the temperature. Equally, you use a plagioclase liquid thermometer from Peterka, and you need to know your water content. So you might actually want to iteratively solve those equations, but that is difficult to do when they are in different environments or different languages or different Excel spreadsheets. And then the final thing is error propagation, which is super important, and I'm hoping we have a little bit of time to talk about today. So we decided to make ThermoBar, put all of the code into Python, so all of the equations are in one language so that the equations can talk to one another. We coded up about 100 of the most popular thermobarometers, hygrometers, chemometers. If your favorite one isn't in there, you can ask nicely and I will endeavor to add it. We're still trying to add models all of the time. And although there is Python code, which if you don't like coding, you might get put off by, you don't have to see this. This is what the source code looks like, but we have wrapped up every function. So this bit of code helps you calculate pressures for amphiboles. You don't need to see that if you don't want to. You can just say you're going to call the function, which is called calculate amp only pressure, and there you go. You're going to be able to do it without interacting with the source code if you don't like coding. One of the things we tried to solve is, as I said, this kind of data input problem. So what ThermoBar does is it reads from an Excel spreadsheet, and it doesn't care about the order of your columns. All you have to do is give it the oxide in weight percent, and then you're going to add a little underscore so you can tell ThermoBar which phase it is. So for example, this column, you're telling ThermoBar, this is the silica content of the liquid. And this is the silica content of the plagioclase. Again, it doesn't matter what order your data comes off the probe in, you just need to add these little underscores based on the phases. And then you can also import other data like the latitude or the pressure you calculated from the melt inclusion. And then that's there ready for you to plot it once you've done the other calculations in Python. Okay, so basically your first step, if you're using ThermoBar, is to format the data as a XLS or CSV and to add these little names so that ThermoBar knows which phase you're giving it. You then have to pip install ThermoBar. So this is basically taking the package, which is stored online through a service called PyPy, and it is bringing it and installing it on your computer. This isn't very big, and it's not going to take up a huge amount of space, and it should just run straight away. So we'll see if that works today. And then you simply have to import it. So in Python, when you see this, import something as something, it basically means you're importing ThermoBar, and because we're lazy, we're now going to call it PT, because we don't want to have to type ThermoBar every single time we do this. And then what we do is we do PT dot and the names of different functions. So in this case, we are importing our data. So we're going to use the import Excel function, and you have to give that function the names of different arguments. So in this case, we're giving it the name of the Excel spreadsheet and the sheet that our data is stored in. What this will do is it will go through your Excel spreadsheet and it will find all of the columns that have liquid in the name, and it'll pull them into a data frame, which is like kind of a Python Excel spreadsheet. And then it'll do the same for clinopyroxene and plage. So it'll basically separate out all of your different phases. And we then extract these separate phases that have been pulled out by just taking the name of the variable. So we called this out. You could have called it like cake. It really doesn't matter. But then you're just going to do square brackets and the name of the phase. So in this case, we're going to pull out liquids. We would also maybe want to pull out plagioclases if that is what we had loaded in. And you would basically pull out whatever phases you'd loaded at this point. And then the data is completely ready to put into any of the functions, just in these 3 lines. So for example, if you wanted to calculate temperature using plagioclase liquid or K-feldspar liquid, what you would do is basically the function requires you to supply the liquid compositions that you want to use. So you would say equals and then whatever you called the liquids in the previous slide. So you can see I called them my liquids and my plagias. So I specify my liquid compositions, I specify my plagioclase compositions, and then the final thing you need to specify is the equation that you want to use. And again, these are all listed in the paper. So here we maybe want to calculate temperatures using Peterka 2008 equation 23. Now, if you were to run it just with those arguments, you would actually get an error from Thermobar telling you, sorry, this equation requires a pressure. So in this case, you would then maybe say, I want to run my calculations at 5 kilobars. And then this would run, and it would give you an output of your temperatures in Kelvin, which you would then have to subtract 273.15 to get them into Celsius. What you might want to do is might want a little bit more information. Say you don't just want the temperatures. You want to know, are these plagioclases and liquids, are they in equilibrium with one another? And you can get additional outputs just by specifying this equilibrium tests equals true. So what this is going to do is it's now going to give you a data frame. This is that Python spreadsheet-like structure. So now you have a column for your temperature that it calculated, but it also tells you whether your plagioclase liquid pair passes the anorthite-albite equilibrium test that Keith Peterka said. And you can see, sadly here, my first 3 do not pass that equilibrium test. So you might not want to use those temperatures because we don't actually know that plage and liquid are recording the same magmatic conditions. If you want to generate your own equilibrium tests, you have the values for like the predicted anorthite content, the observed anorthite content. So you could build your own filters depending on perhaps experimental data where you've tested what the best filters are. Okay, say you want to know temperature and water. You're getting greedy. You want to know 2 parameters about your system. You would do the same thing. You would specify your liquids and your plagioclases, but now you have to give it an equation for temperature and an equation for water. And here we're going to specify how many iterations that we want. Typically, these converge within about 30, but you have that as an option in case you aren't converging. And you can see here, now it's going to tell you the temperature it calculated. It's going to tell you the difference between this temperature and the temperature in the previous iterations. This basically allows you to see that it's converged to within the 7th decimal place, which is good enough. It tells you the water that it calculated, how close the water was to the previous iteration, and then it provides the equilibrium tests again. So in general, when you want to iterate 2 variables, the functions are called like calculate, the phase 1 name, phase 2 name, and then temp hygrom would be temperature and water, pressure temperature would be P and T, and so on. This is all kind of in the documentation, so you don't have to learn these off by heart. Okay, obviously in this webinar, I cannot possibly explain everything that Thermobar can do. So I would, if you're interested in more things, go to the YouTube channel and you can see there are videos of me talking for lots of different things. If you really care about error propagation, you could watch this video. If you care about comparing compositions to the data that was used to actually calibrate these equations, you could watch this video. And then as well, we have a read the docs page. So you can navigate to this. And what this has is it has example Python notebooks for pretty much every workflow you would want to do. So say you want to plot a pyroxene ternary diagram, you would go on the left-hand side and you could download one of these notebooks, or you could do some clinopyroxene liquid melt matching, and you could click on this notebook. So hopefully lots of documentation. Again, if there's something you really want to do that isn't documented, reach out and I will make a notebook and everyone will benefit from that as well. Okay, so I think we should start by actually doing some calculations. So I want everyone to open up how you want to run Python. If you have Python installed locally, you can open up JupyterLab or VS Code or whatever you want. If you do not have Python locally, I'm going to show you an option if you've registered for Victor. So Victor is run out of Lamont. We actually have The two fabulous people responsible for this joined today. So Ina and then Sam, the developer, are on here. They can say hi in the chat to everyone. This is a fabulous resource if you're, say, using Python in classes and you don't want your students to have to do a local installation, because after they've signed up, they can just click this hub portal and then you can choose your server. So if everyone can navigate to this, that would be great. I'm just going to choose a 7 GB of RAM server on CPU, and then I'm going to
still on the PowerPoint.
Oh shoot. Okay, 1 second. Whoops. Okay, 1 second. Thank you, whoever shouted that out. We'll get that. Okay, I'll show that again. Sorry, everyone. So you go to this Victor website. We've posted it in the chat, but maybe Gustavo, you could post it again. You're going to click on Hub Portal. And then it's probably already going to load, but there is an option there, and I put it in the screenshots, where you select like CPU only and then choose the drop down for like 7 GB. And then if people, just so I can like kind of keep track of where we're at, if people could like write in the chat once they've got Victor open or they've got their local Python thing open. So I know it might take a minute to sign in to Victor if everyone does it at once, or you haven't done your authentication yet.
Yeah, and if you have a question, if you're stuck somewhere, there's a breakout room. It's called Help, and like we can get in there and like you can show your screen or something like that. But yeah, just let us know if you are accessing the notebook through your local Python installation or through Victor, and how, like, if you have already been able to sign in.
Yeah, people, and you've got the files, so I'm hoping I'm going to show you how to load the files into Victor, but I don't want to do it until everyone has it on their screen. So if you're planning on using Victor and you're not there yet, could you just type in the chat, wait, in capitals or something, so that I know? And type whether you're in. You can type, I'm in. Okay. Well, I'm going to show you, and hopefully you can keep it in your short-term memory, using local but taking notes of Victor. Okay, so I'm going to make a new folder. So I did that just by pressing this new folder button up here. I'm going to call this Converse Demo. Okay. So then once I'm in this new folder, and this would be the same using other Jupyter servers. So you might have used like the Enki server, for example. You're going to press this Upload Files button, and then it's going to go to your computer, and hopefully you've downloaded the files I sent. So you have one called Converse Example Data and one called Thermobar Intro. So I'm just going to select those two, and then I'm going to open them, and you can see that they will appear. Oh, maybe I can only do one at a time. Hold on 1 sec. Okay, they're both there. So you can see I have the spreadsheet and I have the notebook. So if you open up the notebook, is everyone at the stage where they have this notebook open on their computer?
Yeah, you also want to make sure that your Excel files in the same directory or folder as your current Jupyter notebook.
Where's the... I'm struggling. To make this easier, would people be able to quickly turn their cameras on and give me a thumbs up or a thumbs down? Because I'm like flying blind here as to whether you guys are following along. Okay, keep your thumbs up or thumbs down once you've got your cameras on. Okay, if anyone is still struggling, we have a breakout room. Please join that and we will be able to help you, because I can't help all of you at once. Okay, so the first thing that you're going to need to do if you're running locally or you're running on Victor is you're going to need to run this pip install command. So can everyone see this top cell in my notebook? So I'm just going to run it, and it basically says it's collecting Thermobar, it's checking all the requirements, and here it's successfully installed Thermobar 1.0.54. So that's the version that you're going to need for today, because that's got some of the new functions I wrote. And then what the next cell does is this basically imports the things you're going to need. So it imports NumPy, which is like math in Python, pandas, which deals with these data frames, matplotlib, which you're going to use to make plots, and Thermobar. And again, it's just going to print the version here. And if you have an older version, you will need to run this pip install upgrade thermobar. So you need to make a new cell, run this, and then restart your kernel. So hopefully, again, type in the chat if you're lost. Okay, so the first thing we're going to do is we're going to load in our example data, and we're going to grab it from this liquid only column. So if I just pull across the spreadsheet, you can see what we have here is we have 10 liquids, and we have their major element compositions here, and some other random columns that we've happened to add. Okay, so we're going to pull that, and then you can see what thermobar does is it's grabbed all of the headings that it needs, and any headings that it thinks it needs for some models but you don't have, it has just filled with zeros. So like if you're using the nickel, some of the like nickel thermometers, you might need nickel in the liquid, but if you don't have it, don't worry, you just won't be able to use those models. Okay, so say we want to calculate a liquid only temperature. To start with, you might wonder, well, what does Penny want me to give to this function? So in Python, you can always run help, and then you do pt, which is the name of the package, dot the name of the function, and the names of the function are given in the paper. So if you run this, what you'll basically see is it gives you a list. So it tells you what parameters you need to give it. So you need to give it a data frame of liquid compositions. In this case, this is the my liquids. You also need to give it an equation for temperature. And this is when you have a lot of choice. So any of these equations below, you can run, okay? So you can scroll down through all of these, and you can be like, oh, maybe I want to run it using the new thermometer from Tom Shea, which was calibrated for Hawaii. Okay, so then what we're going to do is we're going to do calculations using that. So we're going to calculate temperatures using Shea, and we're going to do PT, calculate liquid only temperatures. We're going to give it our liquid compositions that we put in above, and we're going to specify the temperature, and you can always copy it from here if you're not sure exactly what one to use. And then we're going to subtract minus 273.15 because most of us think in Celsius, not Kelvin. Okay, so you'll see for the first liquid, you would get a temperature of 1,105 degrees. Now I want you all to try another thermometer. So choose another thermometer from this list, put it into here, and then I want you to type the first number into the chat. So what temperature you would get using a different thermometer. So I want you to write the thermometer you chose and the temperature that you got. So have a go at just pasting another equation into here and seeing how different the answers are. That one gives an error. So you can see here, I chose BT 1993 OPX. And with Python, when you get an error, always read to the bottom. So you can see here it says value error. This OPX equation requires you to enter P. So you'd have to come up and you'd say, okay, I think my stuff was stored at 5 kilobars, and you would enter pressure. And you can see now it solves. So is everyone, people could type so I know that you're getting temperatures. Is everyone kind of here, or do people need help? Steve, are you okay? I can see you're the only one with your camera on. Yeah. What thermometer have you used? Oh, you're muted. Sorry.
Yeah, I'm doing some multitasking right now.
You're doing, oh, that's fine.
Something else just sort of came up. It was a fire, so to speak.
No, has anyone else got a temperature? Or if we're lost, could you please tell me where you're lost so I can help out? Okay, can everyone try running it with, okay, we've got some people participating. Thank you. Okay, sweet. So we're getting like reasonably similar temperatures. Now, what you could do is you could go through and you could change each of these equations and paste them in, and then you could record the results, or you could duplicate the cell. Fortunately, I'm not going to make you do that. So I've written a function called calculate liquid only temperatures using all equations. So that's the next cell down. So if you run that, you will basically see that now you have the temperatures in Kelvin from all of these different equations. So that would allow you to go along and maybe, so for example, in Hawaii, Tom Shea's thermometer was an upgrade of this Heltz and Thornburg one. And you might be interested in like how different they are from one another. So you can see just visually looking at them, they're like this is like 8 degrees different. This one is 6 degrees different. So they're not drastically different. So this can be really helpful if you're like have decision fatigue about which thermometer to use. If you can show that they all give the same results, it really doesn't matter which one you choose. That's within error, basically. Okay. So liquid only is like the simplest example because it's just a single phase. Quite often you're going to have paired analyses. Okay, so if you pull up the Excel spreadsheet, you have CPX liquid composition. So you can see here, can everyone see my spreadsheet? Gustavo, can you see my spreadsheet? Fab. Okay, so you see now you have liquid compositions here, all the way up to here. And then you have CPX compositions further along. So these might be experimental charges where you measured a CPX and the liquid next to it. These might be melt inclusions, or these might be like rim matrix pairs that you've made in a natural system. So now we're going to load in this data. So the only thing we've changed is we're now specifying a different sheet. And in this case, we're going to extract the liquids and we're going to call them licks with CPX. And we're going to extract the CPXs and I'm going to call them CPX with liquids. Okay, you could call them whatever you want. So you're just going to inspect them. So in Python, when you do this .head, this basically allows you to check that the data is read incorrectly. What you might find occasionally is like if the silica content is blank, it's probably because you have like a weird character. So if you've downloaded the data from JPEG, for example, the like file might have a space before the silica content. So it'd be like space SiO2 liquid. So you're always just going to want to check that your data is read in correctly because it can be easy for weird characters to kind of throw this off. So you're going to run these cells. And sorry, just to clarify for those who haven't done this, you run a cell by either pressing Shift Enter or by pressing this run button up here. Okay, and now we're going to calculate pressures and temperatures with CPXs and liquids. So we're going to use, again, if you want to know what equations are available, you would copy the function and you would go help like this. And then you can see that these are all of the pressure equations and these are all the temperature equations that you can use. So here we're choosing Peterka equation 33 and Peterka equation 30, and we're going to want our equilibrium tests back. So you could run this. So you can see you got a pressure of 2.5 kilobars, a temperature of 1350 Kelvin. This pair passed the equilibrium tests that David Neves suggests. And then you can scroll along and see lots of different equilibrium test values as well if you want to. Okay, so I want you to post in the chat now if you are still completely lost, because I'm not getting a lot of feedback from you folks. So if you are lost, please type lost into the chat and either myself or Gustavo will help you out. Otherwise, I'm going to proceed assuming you're all following along and just not saying anything. So, okay, so Darren says, quick question, I have the code working, but what are the rows referred to earlier? Yeah, so each row in Excel is a clinopyroxene. So for the liquid, it would be like liquid 1 would be on row 1, liquid 2 would be on row 2. These might be like different EPMA analyses you've made or different XRF analyses. And in this case, your paired CPX and liquid would be one row. So one phenocryst and its matrix glass would be a single row in Excel. I hope that answers your question. Okay, can folks try this calculation? So we get 2.5 kilobars using Peterka equation 30. Can you try using Peterka equation 31 and see what you get and type your answer into the chat? Okay, so Kata got 2.4, so it's pretty similar. Yeah, so we're getting pretty similar answers. That's pretty good for barometry. Okay, and now let's choose something a little bit more different. So let's maybe use Neve. So this P Neve 2017. So try and do this with the Neve, which is the 2017 barometer that's become quite popular for use in Iceland and the like. And then, yeah, again, type your answer into the chat so that I have some idea people are following along. Anyone got a Neve number yet? Yeah, 0.9. Okay, so that's actually quite different. If we think about P equals rho GH, the difference between 2.5 kilobars and 0.9 kilobars is actually not insignificant. So that's starting to become, you're starting to see one of the problems with thermobarometry is that it's very dependent on your choice of equation. Okay, so let's talk a little bit about, you've got these answers. If you absolutely hate Python, what you can do is you can now take it into Excel, okay, and I'll forgive you. So how you would do that is you would type the name of the data frame. So in this case, the data frame is called PTX CPX, and you can get it into Excel in a variety of ways. Firstly, you can just type to Excel, and you could call the spreadsheet like I love Excel.xls. And if you run this, it will save that data frame to Excel, and now you can take it off in Excel and do whatever you want with it. So we can run that. And you can see what's going to happen on Victor is it's going to appear here on the left-hand side. I can then download it, and then I have it. I have my I love Excel file. And here you go. Here's everything that you could possibly want. No need to spend more time in Python than necessary. So you have all of the column headings. Let's just unwrap the text. And it has all of the input parameters, and it also has things like all the cation fractions, all the components of the clinopyroxene, everything that you might possibly want. So that works great on Victor. If you're running locally, you can kind of do a cheat that I love. It's called to clipboard, Excel equals true. And what this will do, I'll put this in the chat, is this will copy it onto your clipboard, and then you can just paste it into Excel if you already have an Excel spreadsheet open. So that's one way to interact with it. Or you can use Python's plotting functions. And this is obviously easier because you're already in Python. So what we're going to do to start with is we're going to make a histogram. So in Python, to use matplotlib, you're just going to do plt dot and then the name of the plotting function. So here we're going to plot a histogram. And basically how these pandas data frames work is you grab the data frame and then you do square brackets and you take the name of the column. So in this case, if I put square brackets, quote marks, the name of the column, I can extract a column of all my pressures. Or equally, if I take my temperatures, I can extract a column of my temperatures. Okay. So for the histograms, to start with, I'm just going to plot, just copy the top line into its own cell. So you can just see what this does. So now I'm just plotting a histogram of my pressures, and I'm looking at all of the data. So you can see using the Neve equation, this is what I get. So pressures from -6 kilobars to 4 kilobars. Now you might think, but Penny, some of your CPXs didn't pass their equilibrium test, so we shouldn't be plotting them. So you can subsample these data frames. And the way that you do that is you can use this .lock function. And basically what is between these two square brackets is a true or false statement. So I'm basically saying I want to look at the rows where equilibrium tests Neve 2017, so this column heading, where this is true, okay? And we're basically going to get still a list of true and falses. But you might also want to do something like you might want to look at where the temperatures are more than like 1,200 degrees, okay? So anytime you need to just make one of these true false statements, and then you basically do the column that you care about, .lock this true false statement, and then what it'll do is it will plot just the subset of the data. So you can see, considering all CPX liquid pairs, I have a lot which kind of like weirdly negative. And then once I consider only those passing the equilibrium tests, it's brought down the range of pressures. Okay, so I want you to try adapting this code to plot temperature instead. So what you're going to have to do is look where it says P kilobar calc, and instead you're going to plot the temperature column, okay? So have a go at that, and I want you to post in the chat once you've done it. And then the only other thing this code is doing is it's plotting the X label as pressure in kilobar. And actually that Y1 should read number of analyses like this. Okay. So yeah, have a go at tweaking it so it shows you temperature in Kelvin instead. And I don't know if you can put a screenshot in the chat. Let's test that. We can see what people's histograms look like. Nope, you cannot. So while people are doing that, does anyone have any questions they want to put in the chat or anything they're struggling with? Okay, I'm going to show you folks how to do it for anyone that's struggling. So watch your screen if you haven't got there yet. So you're going to calculate, you're going to copy where it says TK calc. I would always copy column headings. So I'm just doing Control C on my Windows computer, because otherwise you can type them wrong. And then I'm just going to paste this into here. I'm going to paste this into here. And I'm just going to change where it says plot X label to T Kelvin. And now do you see this is my temperatures in Kelvin? So put yes into the chat if you've managed to get here. Yay, well done, Claire and Evelyn. I'm getting an error. PT, Alex, is it possible you haven't run your cells? What I would do in that case is basically go back to the top and press all of the cells and run them one by one. Because that indicates that the cell where we define PTX, CPX, this one has not been run. A good question. Okay. Right. Let's move on slightly. Okay, so again, we can actually look at all of the equations. So here we're going to do, okay, so there's a couple of things to be aware of here. There are some machine learning models for CPX, specifically one by Maurizio Petrelli and one by Corin Jorgensen. These models are big. What that basically means is I have to train the model on my laptop, and then I provide like a special type of file. Either it's called a pickle, because it's like pickling data, or another file called an ONNX file. And these have to be distributed to you. Now, PyPy, which is the free service I use to distribute Thermobar, will only let you distribute files above about 100 megabytes if you're a big deal. And they concluded that I was not enough of a big deal for this. So this means it cannot be included in the Thermobar package, these machine learning models, because they are too big. So how we get around that is non-big deal Penny had to make a second package, okay, to distribute these models. So that's what this is doing here. You're basically going to uncomment this line where it says pip install, and then this is basically going to my second package, which contains all of the machine learning models, and then it's grabbing the most recent version, which is this v.004 tag. So you're going to run that, and it's going to take a little bit longer because it's a little bit bigger. Something to be aware of in general, making machine learning models work forever is very difficult. And that is because you train the model on one version of Python, and then someone running it on a different version of Python will actually end up with slightly different numbers. And this is like a known issue. So there's two ways you can get around that. You can use this ONNX thing, which should preserve the versions forever. So basically what you'll see with the models is that I give you two outputs, one using ONNX and one which will change with every version, because the original authors didn't benchmark it to a single version. So I don't actually know what versions numbers they wanted. So when I did ONNX, I just had to like randomly choose one. So you'll see that in a minute. But do you see here it says successfully installed Thermobar ONNX. So this now gives you access to machine learning models. So now that's going to let you run this all equation business. So you're going to say again, calculate CPX liquid pressure, all equations, specify your CPX compositions, specify your liquids, and then press run. And then it's just going through. And then what it's going to give you is basically pairs of columns So this first column is pressure calculated with Neve 2017 and Peterka equation 33 for temperature. It then gives you the temperature that was involved in that iteration. And then as you scroll along, you can see all of the different versions. And then you can see at the end here, we have Petrelli and Jorgensen. And actually, by definition, this all function is using the Onyx version because it should be more stable. So have a scroll along here. How different are the results for pressure? Like, what is the biggest difference? Could people type maybe like the highest? Let's look for the first row. So that's row 0 in Python. What is the minimum pressure and what is the maximum pressure? Got an answer. Minimum 0.96. Yeah, I agree with that. Or it's actually a 0.94 here, but yes, very close. Can anyone see like what is the highest pressures? Yeah, so 0.96 to 4.65 kilobars. How big a deal is that? Do people think that's a problem? Type yes or no in the chat. Yeah, how much difference in depth would that be? So how do we convert pressure to depth? You might be like, well, I don't know, I haven't done that for a while. So we can go to the read the docs. So I'm going to the read the docs thermobar. Hopefully you can all still see my screen now I'm doing this. My computer's being a bit slow, 1 second. Right. And you might want to convert pressure to depth. So let's see what it says. So I've just typed in, okay, so then you can click on the result that it found and you'll find that thermobar actually has a function called convert pressure to depth, okay? So then I would copy this into, sorry, I've lost where I am. Copy this into here. So you can use this PT, convert pressure to depth, and you might want to run the help to find out what it wants from you. So you'll find out it wants pressure in kilobars. It wants a value for the gravitational constant. You might think this is weird, but this is so you can use it on the moon if you want to. And then you can either choose, it tells you either specify a crustal density. So this would be saying like my crust is 2,700 kilograms per meter cubed. Or you can use a variety of published models. So for example, this Ryan Lerner model, this is a density depth parameterization for Hawaii. So it accounts for the fact that the volcanic edifice gets denser as you go deeper. You can also do two-step models. So you can specify like you have a crust with a density of 2,700 and a mantle with a density of like 3,300 if you want to. So let's just do this quickly let's just use the simplest option. So we're going to make a new cell. So we're going to say convert pressure to depth, P kilobar equals, and then what you're going to do is you're going to grab this PT all and you're going to choose an equation. So here I'm just going to choose pressure from David Neve. So I'm going to paste that in. And then I'm going to use a crust density in kilograms per meter cubed of 2,700. So what that basically does is it tells me that that top row, 0.96 kilobar, is about 3.6 kilometers. So I want you all to do the same calculation, and I'll paste this in the chat, but do it for that equation, which gives the highest pressure. So do it for this Peterka equation 32C, equation 34. So that's the code. So you'll just have to change the bit between the quote marks here to do it for a different equation. So have a crack at that. Anyone got a depth? Anyone out there? Okay, so you just want to scroll along this data frame and just copy the name of the equation, and you're just gonna put it in between these square parentheses like that, and then run. So, oh, we have life. Oh, for some reason you can't copy and paste the petroleum there. Alex, when you say that, does it not work, or does it just, you mean you can't, your computer doesn't let you copy? Let's try what happens. Oh yeah, you get an error. Oh, that's because I didn't copy the bracket properly. It does not work. There is an error. Right, we'll look into that. Hold on. It's probably because there's a nan, which we can probably fix. So let's just try what happens. See, oh, you get an error. I do not get an error, interestingly. Try taking this code. It might be, do you actually have numbers in your column for Petrelli? Because if you don't, it indicates that maybe this package didn't install properly. Or maybe you can. Oh, what does the error say, Alex? Can you paste it into the chat? Ah, it's because you've pasted two columns, Alex. So yeah, you basically it's just your copy and pasting being stupid. It's not your fault. You would just need to make sure that you're just copying the column headings like I am here, rather than the two columns together. So syntax error indicates that you've basically given it a column that doesn't exist. Okay, so that kind of shows, like, you know, how you can do various things. I'm just going to show one more useful thing that you can do. So has anyone ever wanted to plot like a ternary diagram? Ternary diagrams, ever wanted to do so? Well, you can do them in Thermobot, even if you haven't ever wanted to do it. So what you basically do is you take this function, pt turn points pyroxene, and this is going to calculate the three kind of coordinates on that ternary plot space for your CPX compositions. That's going to be the first step to plotting it. And then we have this plot function. So this is the function pt plot pyroxene classification. And to start with, we're just going to act simply, and we're just going to specify the figure size. Okay, so this is going to specify that it's 10 by 5. So you can run this. You can see it hasn't got your data on yet. And that's because we're going to build up working on the plot that we want before we put our data on top of it. So that's a simple figure. What else might you want to add to this plot to put it in a paper? Can someone type in the chat? What is typically put on these ternary plots? Labels. Yes, correct. That is the right thing to say. So if you want labels, then you just simply add the argument labels equals true. And again, you'd know that these arguments exist by reading the documentation, by doing that help.pt plot pyroxene classification. So here I'm saying I want labels. I want the font axes labels to be font size 20, and I want the internal labels to be font size 12. So you go, now I've got a label plot. Say you like really want them big, you might want to change that to 20. Now you can see Hedembergai is like escaping out of its thing. So you can either make the plot bigger to solve that problem. There you go. So you can play around with various things. You might also want a grid. So here I've got the same as above, but I've just added major grid equals true and minor grid equals true. So various ways to customize this plot. And now once you're happy with how it looks, you can add your data. So what we've done is we've just copied this line of code. And then you're just going to basically, the second line of code specifies what you're plotting. So these are the coordinates that you calculated above, and then various things. So this is the marker edge color is black. K is black in Python. You want to do that marker as a triangle. You want the marker interior to be red. And you want, if you want it labeled, you'd maybe specify it as label 1, or maybe you'd label this like Hawaii or whatever. And then S is size. So 90 would produce. You can see now you have your ternary plot with red triangles, which are size 90. Just so you understand, when you're running Python, you will commonly see these pink warnings. These are not errors, they're warnings. You can typically ignore these. This is basically because I wrote this with an option to color by a third variable, like you can color by jadeite content or magnesium number. And because you're just specifying that you want these symbols to be red, it doesn't. It's a bit unhappy, but it's going to be absolutely fine. And what you can see is that it's made you a figure and it saved it. So again, I can download this figure from Wieser, or this is going to be locally on your computer, and I can open it up. Hopefully it'll open. You can, oh, my computer doesn't want to show it. It is there, I promise you all. It's just not popping up because of Zoom. But you have a figure, okay? So you can get figures, you can get spreadsheets, etc. out of Thermobar. Okay. I just want to take a second to kind of like step back and think a little bit about thermobarometry in our final few minutes. So I really want to encourage you to think about what questions you can answer with thermobarometry. And hopefully you can all see my slideshow. Can everyone see my PowerPoint again?
Yeah, we can see it.
Right. So here I've compiled crustal thicknesses around the world. So mid-oceanic ridges, your mean crustal thickness is about 7 kilometers. As you go to ocean island basalts, you have a volcanic edifice built on top of that oceanic crust. So you're pushing down to like maybe 14 to 30 kilometers. And obviously in arcs, you have a much thicker crust. Now, if we think about the errors of a typical thermobarometer, we need to think, what questions do we want to answer? So in a mid-oceanic ridge, we might want to say, is our magma chamber in the upper, the middle, or the lower crust? To be able to do that, based on the fact the pressures are only spanning 2 kilobars, you realistically need a precision of about 0.25 to 0.5 kilobars to be able to answer that question. In Hawaii, you could maybe get away with a precision of a kilobar to start answering the questions you care about. And in arcs, where the crust is thicker, you could still say upper, middle, lower crust, even with like a 2 kilobar error. But typically the errors on these barometers are on the order of about 2 kilobars. So this is what the error bar looks like relative to the thickness of the crust. And you can really see that with that error bar, you cannot resolve anything about storage at a mid-oceanic ridge, because the question you are trying to answer is too accurate for the method that you are trying to use. Keith Paterka famously said, CPX barometers are not a penknife, they are a chisel. And this is why you would not want to be like carving something intricate with a big chisel. And this actually represents the fit to the calibration data set. So this is actually the data that was used to train the model is only fit to 1.7 kilobar. And this is where you know temperature. In reality, if you look at data that wasn't used to calibrate this model, the error is actually 4.2 kilobars, which is on here, like down to about the bottom of the crust in OIBS. So please, when these methods are useful for some things, but you have to think about what the error means in terms of the scientific question you're trying to answer and how thick your crust is fundamentally. Okay, so yeah, that's me done, and I hope that was useful, and I'm really happy to help people. If you're stuck with something, send me an email and I'll try and get you going with Thermobar.
Awesome. Thank you so much, Penny. Yeah, I wasn't familiar with Thermobar. This is an awesome tool. And like I just love how easy you made it with like especially downloading these data frames into Excel files. I think it's very practical. So is there any question? I know it's already the end of I mean it's already 5 p.m. here in Eastern time zone, but if anyone has any question, can let us know. Just... Okay, Michael, you have a question?
I do. So I'm very new to coding. And I was curious, say you have a volcano that doesn't have a model that's specifically designed for it, like you mentioned that Hawaii model. What are some like kind of, I'm a petrologist, so besides petrology factors, what are some things to consider when thinking about models to fit to different volcanoes or volcanic regions?
Yeah, that's a great question. What I would want to do is look at the compositions that you're expecting in your system. Okay, so say you're working on a weird alkaline volcano. What you'd want to do is take your liquids and your CPX compositions, and you would want to, Thermobar has all of the calibration data sets for different models in it. So, and you have ways to it's just like a one-liner code to plot your data on top of the model. If the model calibration in sodium potassium space does not overlap with your data, it is not an appropriate model. So that, and I would, if there are like 3 models which overlap with your data, run all of them. And if they give different results, then that might be the best that you can do. People are suggesting more and more that we really need like volcano specific places. Like these CPX liquid relationships are so full of uncertainty. Maybe from a thermodynamic perspective, it's unreasonable to expect a global solution. And in that case, you need to make friends with an experimentalist to calibrate a model for your system. Or we all need to make more friends with experimentalists and have them do more experiments. It is a really difficult problem. And this is why, if you don't know, the only thing you can do is compare different models, which would all be an equally valid choice. And if they give vastly different results, it might be that you just don't know until someone comes and does a volcano. It sucks that that's the case, but I think that is the reality in a lot of places, particularly in weird systems where there's not a lot of calibration data. Like wasn't a lot for rhyolites in Yellowstone. So Cara Brugman, Christy Till's student, made her own thermometer because she realized all the existing ones were absolutely useless and they were just going to give her like nonsense answers.
Yeah, nice question, Michael. Any other question in the chat, or maybe you can unmute your microphone? All right. I think we
Can I
can.
just say one more thing? If you are scared of Python, please make use of Victor. It is amazing. You don't need local installations. I know they run great workshops. You can just upload files. Someone gives you a code, and it's literally just like pressing Shift Enter or pressing play. So don't be scared of Python. I didn't know how to code in Python before I wrote Thermobar. So you have to start somewhere. And Victor is really an amazing place to start because you don't have the issues of local package installation, which is, I would say, the biggest activation barrier to get going in Python. And they have videos on their website as well.
Yeah, so you can use Victor for any other type of resources. Maybe Sam or Aina, you wanna talk a little about Victor? I'm sorry to put you on the spot.
No, it's fine. Is there anything specific you want us to highlight?
Uh, Maybe like the kind of models that you can do.
Yeah, sure. We have models for right now. So lava flows, gas, PDCs, a little bit of geochemistry and petrology. Right now, our entire goal is basically to make the platform usable for everyone within like the volcano science community. So if if there's more geodesy that you need, or if there's a model that we don't have, and you have been using a lot, please let us know. We'll add it. We also have a forum, or not a forum, sorry, we have a documentation page that I'll put in the chat in a moment so I don't have to multitask. And then yeah, that's kind of it. So if you have any interest in looking into the platform, I think I saw a good number of you sign up, so go poke around there. As I said, there's videos from that from our main page, which is just victorproject.org. There's videos, there's documentation, there's other like blurbs, abstracts. So that should give you a general idea of what we have. And if you have any other questions, feel free to email or like message in the chat.
Thank you, Sam. All right. And before we go, actually, I'm gonna share my screen. Just gonna say, we have these webinars running every other week, until March or April. You can check the whole schedule on the website. It's on the screen, converse-er.org. And our next presenter is going to be Carmen Jaimes Viera from the National Autonomous University of Mexico. And she's going to talk about distributed volcanism in central Mexico, spatial-temporal evolution, and volcanic hazard assessment. So make sure to join us. If you have registered for this session, you are automatically registered for all sessions. You can use the same Zoom link, and you're gonna get a reminder on the same day of the upcoming sessions. Michael, you have a question?
One quick shout out as well. If you would like to be a future presenter, please send us an email at converser@gmail.com. We'd love to have you. There's so much cool work that's being done in this community, and we'd love to spotlight it.
Yes. And we have a full schedule for this spring webinar series, but we are looking for speakers for our fall webinar series. So yeah, you can contact me directly, or you can use the email address that I'm putting in the chat. Thank you, everyone. And thank you, Penny, for that awesome presentation.